So we'll do kind of a 180 degree here. We will not talk about diagrams or Monte Carlo or strongly correlations. We will do it very basic. Yeah? We will talk about machine learning and how machine learning is being used to accelerate our workflows. This will be DFT. I will not talk about DFT either. Okay, so please be gentle. So let's start. So you probably have noticed that we are in the middle of a revolution. And I'm not talking about physics or material science here. I'm talking about society. I guess all of you use ChatGPT. They have 800 million users currently. So I guess you're all one of these 800 millions. And this changed our way of life. Of course, we are part of the society, so it's normal that also we are changing our way to work, right? And some people call this actually the fourth oh, sorry, this doesn't work, yeah. The fourth paradigm of science. So data-driven science to be compared with empirical science, theoretical science, computational science. Of course, this is not meant to replace all of this. This is also a misconception. This is on top of all of this. Right? And everything is necessary. We're not going to get rid of computational science. We're certainly not going to get rid of theoretical science, and much less of experiments, right? Physics is still an experimental science, right? And this was recognized last year, to great surprise, I think, of everybody, that 2 Nobel Prizes for machine learning in the same year. This is kind of unique, right? You all know this. And I will discuss how we can use these techniques. And in this talk particularly, I'm just going to talk on how to use machine learning to accelerate material science. I'm not going to talk on how to use artificial intelligence to improve our models, for example. That can also be done. But this talk is purely about acceleration of things that already existed. Moreover, whenever I talk about results, they will be DFT results. Yeah? So we're just going to accelerate the path to arrive at the stage that we do DFT or whatever other method you want. And so there is no extra error that is induced by machine learning, okay? So what do we need to do machine learning? So first, we need data. Now, this is the most boring part. Data probably accounts to 90% to 95% of the time that someone spends doing machine learning. Without data, you don't do anything. It's a data-driven approach. And I can also assure you that every single bit of data that exists publicly has been used to train a model. So if you want to do machine learning, you're not willing to put the effort into the data, you're probably not going to go very far. So this is the first big message. Machine learning is mostly about data. Now, data, ideally, I would like to have experimental data. Experimental data, after all, physics is an experimental science, right? But unfortunately, the experimental data that we have access to is usually very patchy. It's a large collection of usually very disparate things. The quality is also can be very good, very bad, but it's even hard to know sometimes. And it turns out it's really, really hard to use it for machine learning approaches. And this is not only in our field. I've heard people complaining about this in many other fields. So it's really hard. So what is the alternative? The computer scientists call it synthetic data. Synthetic data is data that is produced by another model, right? In our case, DFT, ab initio codes, okay? And when possible, we will try to throw in some experimental data when possible, although this is not very easy. To do all this and to get enough data to do machine learning, we need automatization. So we need automated workflows. You don't do machine learning with 100 samples. You can, yeah, but that's not really the heart of it. That's not really where it shines. It shines when you really have a lot of data. So in our case, let's say millions, hundreds of millions of data points. To get them, you obviously have to have automated workflows. We cannot have someone pressing the button every time. That doesn't work. Then we need high-performance computing. That we also have. And finally, ideally, all that stuff will go into open databases. This is not the case anymore in the community because the big companies have entered the game, and they have their own data that they don't share. Google, for example, has. I will talk about it later. So this is the outline of what I'm going to talk about. First, I will show you what we do in practice, so our workflow, if you want. And in the middle, mixed, I will talk about some of the machine learning models that we use and that we develop for various aspects. You will see that's not one model, because we need several of them, but I hope you get an idea. Then I will tell you what we want to do, which is maybe a stupid utopic idea, but we would like to get all compounds that could eventually be synthesized in a lab. Compounds, by compounds, let me also be clear, I mean inorganic compounds, excluding glasses and alloys, so excluding disorder. I'm not saying these glasses and alloys are not interesting, not that they're super interesting, but we have to start somewhere. And crystalline stoichiometric compounds are the simplest point where we can start. Okay, yeah?
Or did you mean to say all compounds that have been made in the lab?
No.
There's a very big difference.
It's could.
Could. So you're including hypothetical, possibly unmakeable compounds.
We will try to increase the probability to search in the material space such that the probability that they can be synthesized is maximized in some way. But I will come there. I will come there. Although this is not, I cannot give you a yes or no, we can or not. We'll be conservative in any case. So we prefer having false positives than to have false negatives. Yeah, that's the idea. Then I will go to conventional superconductivity. That's the easy one, right? Electron phonon. And show you what we have done in the last years about it, and then I will conclude. So let's start. So what we do in practice? Well, we need to start our loop. We need example materials. So we need to have something that suggests us compounds. Compounds means a crystal structure and the chemical composition, of course. Sometimes we just grab a crystal structure, whatever, that can come from whatever, and then we just systematically change the chemical composition through the entire periodic table. For example, for a ternary compound, this gives 500,000 possibilities. 500,000 is not so bad. Otherwise, we have other ways of getting suggestions. One of them is our generative models. Maybe you heard of MatterGen from Microsoft. It was a big thing around 1 year ago. So we don't use MatterGen. We have our own generative model. I'll talk briefly about it. But the idea is something that tries to suggest compounds based on some pre-known distribution of compounds. The crystal structures that come out from here are usually not very close to dynamical equilibrium. So we have to relax them. We could use DFT, but relaxing, so nowadays we are generating around 500,000 compounds a day. So this gives 500,000 compounds a day. So if I would like to relax them with DFT, I would certainly not be able to do 500,000 a day. So we resort to another machine learning model. They're called universal machine learning interatomic potentials that basically are surrogate models for DFT. I will talk also briefly about them, and then I will explain. So this actually works extremely well since 6 months ago. Yeah. You can get essentially relaxed DFT-level geometries with 10,000 times faster or 100,000 times faster than DFT. It's really amazing. Then we would like to predict their stability in some sense. The simplest stability we have access to, besides dynamical stability or kinetic stability, that's also easy to check, is thermodynamic stability. And this is just total energies. It's very crude estimation, but it's what we can do. We could calculate it, but we don't. We use another machine to predict it. Yeah? Yes?
Stability relative to elements, relative to known binaries, relative to known ternaries.
Relative to all 160 million compounds we have in our database.
Okay.
Yeah, so.
It's redundant. If you only have 3 elements, you don't need to do one.
Sure. We don't. But if you have, I don't know, a quinquenary compound, you have to find all the possible decomposition channels and compare to each one of them. Yeah, so that's what we do. Then, if we're happy with it, and we are usually conservative, so if something is slightly unstable, we take it anyway. We DFT it. So we do a relaxation in DFT, calculate the energy, calculate the band structure, whatever you get from a DFT calculation. And then if we're happy with it, then we have a series of machines that predict properties. Properties could be the transition temperature of conventional superconductivity. It could be the dielectric constant, the elastic constant. So we have models for a series of things. If we're happy with that prediction, then we validate it using density functional theory, perturbation theory, density functional perturbation theory, whatever is necessary. If we're happy with this, then we will try to approach our experimentalist friends and try to convince them that there is something interesting here. Now, all these models, they yield, so all these DFT calculations and the perturbation theory calculations, they yield data. And all these models require data to be trained. So all that data is put in our database. We have a database. It's called Alexandria. And it is by now the largest academic database of DFT calculations for materials. And I always say this. I say academic because Google has a larger one, a little bit larger one. So we have around 7 million compounds. Not all of them are actually released. I think the current version that is released has around 5.5 million compounds. Google should have around 10 million.
This is also transformer?
Like, excuse me?
The way they generate is transformer?
No, here it's everything, but these are the DFT ones.
These are the DFT.
The DFT ones. Yeah? We actually have a table also. We have a database with universal machine learning interatomic potentials. We have, I think it's 161 million now, possible compounds. Yeah? Of course, most of them are hypothetical because there are only 50,000 compounds in ICST. So we only have these 50,000 experimental ones. The rest are hypothetical compounds that the machine came out with. So this is free. You can download it if you want. There is no user interface, so you will struggle a little bit, but that's life. For you to see how this is evolving, so this is the year, and these are the number of DFT calculations that are added to the database per year. And the green ones, the dark green ones, are the compounds that are close to this thermodynamic stability. So these are the good ones, the ones we like. And what you see is that over the years, so first there were very few. Yeah? Now, a large fraction of the compounds that we try, they are close to the convex cell. And the reason is that all our models improved a lot during the years because we had more data to train them. And now they're really good, so we can easily separate the good ones from the bad ones. Maybe, yeah, I'll give the orders of magnitude afterwards. Very briefly now talk about some of these models for you to see also the evolution of the field. And we're talking really, some things didn't exist six months ago, so I think it's interesting. Start with the generative model. So the generative model, the idea is to give us suggestions of materials following a certain training distribution, right? So what we do is actually very simple, much simpler than MatreGen or other models. Our description, so the most difficult thing is to describe a crystal in the sense that the computer can understand what it is. And in this case, we use a very, very simple representation. We use a string to code what the material is. And this string is based on symmetry, on space groups and Vikov positions. So you will see right away. So for this thing that is here, we start by saying it's a ternary compound. E whole low, this means it's close to thermodynamic stability, so in the training set, right? Then it has lithium, oxygen, copper in the ratios 1, 1, 1. In space group 139, this is a code for the Vikov positions. And then go the free parameters. Yeah? So each space group will have a certain number of free parameters. Each Vikov position will have a set of free parameters. And here they are. We do this to the few million compounds we have in our database. And we use it to train a transformer model. So it's like ChatGPT. It's the same thing. Yeah? It's the same architecture. So it's well known in the community. You don't have to invent anything. You can even get pre-trained models if you want and just retrain them with this thing. And then in inference, you start by writing, I don't know, ternary or quaternary, E whole low, enter, and then the machine completes the string. Yeah? It takes 20 milliseconds to complete the string. And so you can do one new compound per GPU per 20 milliseconds. That's the idea. It's not very hard.
So I have a question here. Sorry. Yes. So you're just treating this as text, and you tokenize it as you tokenize language, and
You
that's
just
it,
tokenize it.
right?
Yeah.
And then it's like language, and
Yeah.
that's it.
Yeah. You can grab Llama,
Yeah.
insert this, you train it in a couple of days, and it actually works.
Okay.
It's very simple.
Thanks.
Yeah? You can. You can. You can even add here TC equals something, and then it's called conditioning. Yeah, you can. The point is that our approach is a bit different. We first want to discover all materials that could be synthesized, and then we search for properties. So we do it the other way around. We don't search specifically for a material with a certain property. First, we search for materials, and then we check the properties. You could. So the experience in machine learning is the more data you have, the less you have to think. And we have so much data by now that just by writing lithium, the machine can understand what is lithium. And so if you don't have so much data, you really have to go through those descriptors, as in physics they are called, right? We have passed that stage. You don't gain anything by trying to add more information. That's the reality of machine learning. Yeah. So I want to give you an example, just because I'm sure some people here will know what I'm talking about. There is a competitor, right? There is crystal structural prediction that also generates structures. And I have here an example. It's hard to see, but I hope I can show you. This is a chemical system, so this is a phase diagram of a compound that both us and Chris Picard studied with the structural prediction, because there is a very interesting superconductor around here. And this is what came out from structural prediction. And the other day, I actually wanted to plot the phase diagram, and I got this. And it's different, right? See, here there's 1 point, and here there are these 2. So there is something that showed up here that was not in the structural prediction. This actually came automatically through our generation without looking specifically at this chemical system. It just came out. And this is something that has 40 atoms in the unit cell. So you will never get it in structural prediction. So I'm not saying this is a replacement for structural prediction, but you can access regions of material space that you cannot with structural prediction, especially things with a lot of atoms. So we were kind of happy. Next step, the universal machine learning interatomic potentials. This is perhaps the greatest success of machine learning in material science. They are data-driven models that can accurately predict forces and energies and stresses. And you all know these are interatomic potentials. The novelty is that they work across multiple chemical systems and structures. So they are what in machine learning are called foundation models. They are trained once, and then they can be fine-tuned if needed. But the model is trained once. It will not have to be retrained. This was kind of a dream. The first one appeared in 2021, didn't work very well. Now it's no longer a dream. So key features, they're transferable. They have very high accuracy compared to the training data that is DFT, of course. They are fast they are between 10 and 100,000 times faster than VASP. That's the number. And they scale linearly with the size of the system, not cubically. And they should be generalizable to unseen systems, of course. Problem, we need large databases to train them. We really need a lot of data to train them, of ab initio calculations. And we need these databases to include diverse structures and compositions. If you do not have, I don't know, certain class of structures, you will probably not describe them very well. Maybe it will not be a disaster, but it will certainly be worse. And of course, ideally, we should have multiple thermodynamic conditions. And this is actually something one of the things that is lacking, that there is no pressure in the data, yeah?
So if I discover a new crystal structure, which we do sometimes, you're then saying this will have trouble.
No.
Okay, because it sounded like you said that if it has no information about a given crystal structure, it will have trouble.
Not about the crystals. If, for example, the chemical environment of the atoms is somehow present in another crystal structure or with chemical elements that are not the same but similar, the machine will know about it. What I mean is that, I give you a very specific example. You put 100 GPa.
Yeah, super high, right? So it's unprecedented.
So if you don't add any pressure, any data with pressure, they will give you something, because some structures are a bit more compressed than others. But the quality goes down with pressure. That's as simple as that. Yeah? I don't know. There are 4 hands.
I can go first.
Yeah?
Do you train that, like, I know it's a foundational model, but you trained that or someone else did and off shelf?
So I will show you.
You talk about the training data, right? Like, of course, if you get better training data, then you have to create a new foundation model, right?
Next slide.
Okay.
Yeah.
Yeah, so, I don't know if my button is
Pushed it.
already pushed it, okay.
No, you didn't.
Okay, good. So, you say it's transferable. So, you have does that mean you choose a different element and somehow, you enter the element into your model, right? It has to know what you're doing, right?
By transferable, it means it should work for unseen examples. So for example, different crystal structures. Of course, all chemical elements are represented in the data, so it doesn't make really much sense to talk about different chemical elements, but different structures that are not there. For example, two-dimensional, you train with three-dimensional systems and you hope that two-dimensional systems come out reasonable.
Right.
Yeah.
Does it look like a classical interatomic potential in the end? Or?
No, it has between 40 and 80 million parameters.
Okay, but still, that's an interatomic potential.
It is an interatomic potential, yeah, of course.
Used for MD or anything.
Exactly. Yeah, exactly. So, but I'll give more. Let's go here. So there is a leaderboard. Yeah. Oh, yes. Sorry, there is still.
If I train my data on symmetry group 1 to 100 and ask it to predict materials in symmetry group 225, it won't be good.
Well, I think the other way around would be more complicated.
Once your subgroup, maybe, yes.
Yeah. So.
Once you train from S2 hybridization, you will never predict S2 hybridization.
No. But you also have to be careful what it means it doesn't work, because it's not a yes or no. There's a distribution, and there's a distribution of errors, right? So the error will be larger. If it will be qualitatively wrong or not, it depends, right? But the error will be larger. This is the only thing I can say. And you have to try. Well, can I continue? So there is a leaderboard for this universal machine learning interatomic potentials. I put here the ones from, this was from September. I don't know if it's the same. This changes very rapidly. I just want to point to you 2 things. First of all, this is the best, isn't? This is an organization that made it. Do you know what this is? Meta. Yeah, Meta has by far the best universal machine learning interatomic potential. The other ones are not much worse, the ones that are here. I will not go through it. The other interesting thing, these are the training sets. They're always the same. Why? Well, OMA 24 was made by Meta. They published it. They gave it to the world. 400 million hours of CPU. These are trajectories from the materials project. It's actually relatively small as a data set, but it's still used. And this is us. This is us. So this is the data that there is. So you can do whatever machine you want. But very likely, your error will be somewhere here in the middle. Because, I mean, if you have enough data, the model is not very important. If you have little data, the model is very important. But if you have, so here there are hundreds of millions of DFT calculations that are in these 3 data sets. So when you go there, it doesn't really matter what model you have. For as long as you have enough parameters, it's fine. This is the number of parameters, by the way. Okay? They are not huge. See, 30 million, 10 million, 25, 25. So they're still way, way, way orders of magnitude below ChatGPT and things like those. So very quickly, we have then other machines to predict properties. I will try to speed up, otherwise we'll have a problem. I mean, anything that you can imagine. This is just a sample. The interesting thing for here is TC. I said conventional TC that I will talk afterwards. The mean of the test set, of the data set is around 6 Kelvin that was used to test. Our error is 2 point something Kelvin. So this is what you would expect. But I will show you. The errors here are much smaller because this is trained in 4 million, I think it's 4 or 5 million sets. For TC, we have 35,000. And so the error is around 30%, which is, well, it's OK, I think. Now, let's face the beast. Stability. What can we do? I mean, it's not what we do. What can we do? Because we cannot do so many things, believe it or not. Our main correlator, and this is the property that you have that still correlates the most with synthesizability, either you like it or not. This is like that. Is the famous distance to the convex hull. So I don't know if you're aware of this concept. So I will just go quickly through them. And the easiest way is to use an example. This is a binary phase diagram. The vertical axis is the formation energy. Here is composition. Okay, so this is A, this is B, whatever A and B is. And each compound has a formation energy, so it will be a point in this diagram. So for each composition, that gives you the X coordinate. For each crystal structure, you will have an energy, so you'll have points here. Now, if you have a mixture of 2 substances, the energy of the mixture is the linear combination of both energies. So it's straight lines, right? So if you have a point here, the linear combination of A and AB2, it's here, is lower in energy than this. So this is not stable, because this would gain energy by decomposing into A plus AB2. The compounds that cannot decompose are these, and they form a convex hull. So it's convex, has to be convex. And it's called the convex hull that is a hypersurface in n-dimensional space, where n is the number of chemical elements. Actually, it resides in a regular simplex of n vertices. That's material space. That's the mathematical definition, OK? And what we do is to calculate these lines, this hypersurface. The distance, so what happens if we find a compound here? Well, this means that this compound doesn't decompose, so I have to redraw my convex hull. And that's what we do in practice. Now, thermodynamic stability doesn't mean much. It does mean something, but doesn't mean much. You have thermodynamically stable compounds that cannot be synthesized, and you have thermodynamically unstable compounds that can be synthesized. But the distance to the hull, if you go positive, so the probability that you have to synthesize a compound decreases very rapidly with this distance, very rapidly. You cannot be 1 eV above the hull. You cannot. 1 eV, just converted to temperature, it doesn't work. The only exception is that there are some compounds you can synthesize at very high pressure, and that you can quench them, and they can be half an eV above the hull. Yeah, this is the only exception. Yeah? So the way is by using experimental formation energies or reaction energies, which in this context they are similar. They give similar information. And what we know is that the error that we have in our distances to the hole is of the order of 70 millieV per atom, but most of the error is in oxides and fluorides. Okay, so this is the number you have to have. 50, 70 millieV per atom, and most of the error is not in intermetallics, it's not in sulfides, it's in oxides and fluorides. Those are the things that have the most error. But there is the other side of the coin. The experimental results of formation energies, they don't have a very small error. So it's also very hard to know what is our error. Then the other problem is that most compounds are not stoichiometric, and most compounds are not, you always have a little, very often, of stoichiometry. Often you have oxygen vacancies, copper vacancies, and oxygen vacancies can easily give you 50 millieV per atom, 100 millieV per atom. Entropy effects, vibrational can give you 10, 20 millieV per atom. Configurational disorder, if you don't go into high entropy alloys, gives you another 20, 30 millieV per atom. Yeah? So these are orders of magnitude. So what we can tell you, if something is half an EV above the hole, traditional synthesis methods will very likely not get it. This is what we can say. So it's easier to discard materials than tell you that these are the materials that you can make. So let's, I have here an example that I found curious because so we do systematic searches for materials. And so fixing the family and going through the whole chemical space. And this is one of the high-TC prototypes. So it's an orthorhombic structure, so it's the 2448, that's how you call it. I'm not really knowledgeable of the nomenclature of the. So we did so we put here in this position all chemical elements, all chemical elements, all chemical elements, and all chemical elements. So it's around 50 million combinations. That's not a problem. We can do that. We use machine learning to accelerate. We go through all of them. And these are the compounds in order that we find in this crystal structure in order of distance to the convex hull. And on the right, you have if it was synthesized or not. Yeah. So it's pretty good. This compound, I found it was only tried to be synthesized once, apparently. So the no is provisional. The strontium compounds, you see they are less stable than the barium compounds. It looks correct because you cannot really make strontium in this structure. And then calcium, I put the calcium here. This is the lowest compound with calcium 2 so we were 84 millieV above the hole. If you want other curiosities, if you would like to make one with silver instead of copper in this structure, you pay 58 millieV of tax. So probably you cannot make it. If you put nickel instead of copper, for fun, in the same structure, you pay 120 millieV. So it doesn't mean that there are no compounds with these 4 chemical elements. They will just not be in this stoichiometry, and they will not be in this structure. That's the only thing that this means. Okay? Even if the electronic structure, I think 90% of this room will tell you that the electronic structure of all these things in the FT is wrong. But the energies are not completely wrong. This is what I mean. So we did a lot of searches. I have here a few examples. We looked at all 135 Kagome compounds. We found very weird compositions that seem to be stable. So this here, for example, is with cerium in the antimony site, and the osmium, ruthenium, cobalt in the vanadium sites. And you can do weird things like mercury, cadmium, tellurium, indium, lead, and tin and bismuth in the cesium site. I don't know if this makes any sense, but the machine says it's stable. Well, DFT says it's stable. This is another Kagome family. They're actually insulating compounds. There is the sample here. Actually, these things, some of them at least have been made. And again, the same story. We can go through all possible combinations, and we can say which are the most likely or not. We also did, and this is from Emilia's group, a series of other Kagomes. So we have hundreds or compounds that apparently are stable. We don't know about superconductivity, of course, but at least we can tell you there may be other compounds, and we can see if the flat bands are closer to the Fermi level or above the Fermi level. Those things we can say. But let's go to superconductivity. I think it's about time now. And as I told you, conventional. I'm not going to move away from conventional superconductivity. So we can say unconventional compounds if there is a chance of them existing or not. Nothing about superconductivity. Here we can go further. And we have to play again the game. So what did we do? We did the density functional perturbation theory calculations for around 100,000 compounds. We're talking, I don't know, around 100 million hours of CPU or so. You can check how much that costs if you want. Of which around 35,000 are dynamically unstable. So most compounds we have are dynamically unstable, which is maybe not surprising also. Now, what can we do with these games? We can plot distributions. And this is really fun, I think. So this is the distribution of omega log. There is 3D compounds and 2D compounds. We have much less 2D compounds calculated. I think it's 1,500 than 3D, so the statistics are not as good. And this is lambda. What do you see? Well, very beautiful. This is a skewed Gaussian distribution. I don't know why. If some of you knows more statistical physics than me, I would be really happy to see if there is any fundamental reason for this to be skewed Gaussians. And this has a fat tail. So omega log has a fat tail. Lambda has a fat tail. Actually, all the distributions I plotted up to today of every property that you can imagine has a fat tail. Often they're not skewed Gaussians, they're weirder things even, but they all have fat tails. So what we want, we would like compounds that are, I don't like to call them outliers. I like to call them extreme values of the distribution. Okay, I think it sounds better than outliers. Now, this would be a great thing for superconductivity, right? If you could grab a compound with omega log here and lambda here, this would give a very high TC. But you already know the problem is that these two distributions are not uncorrelated, right? Large values here usually anti-correlate with lambda and vice versa, right? That's the problem. The other thing is that if you now plot the distribution of TC, I don't have it here, it doesn't follow a skewed Gaussian, it follows an exponentially decaying distribution, more or less, with a fat tail that we don't have enough statistics to know how it decays, but there is a fat tail. Yeah? Yeah.
Data, and I just, for the compounds I know exist, and I plot the distribution of lambda and omega log. Do I get these log normal distributions?
I don't think you will get a lot of data because there are not so many compounds that you actually can, you know. So I don't think you will have such nice statistics that will allow you to see how the tail looks like. It's an interesting exercise, sure. It was very humanly time-consuming, but I don't think you will have enough statistics to see a real distribution, if you know what I mean. Yeah.
Okay.
Yeah?
This is TC without Coulomb interaction, right?
This is Allendine's formula. But in the cases that we find interesting, then we do either fully anisotropic Li-Ashberg with a mu star, or DFT for superconductors that doesn't have a mu star, right? So and doesn't have problems with the frequency. So the
So far you're dealing with lambda and omega.
yeah.
Then TC is coming out of the...
TC will come out either through Allendine's or through Li-Ashberg or through DFT for superconductors. Then it depends on how interested we are in the compound and how much time we want to spend on it. So this is the summary of TCs. So there's no distribution.
Miguel, I'm sorry, can I ask you
Yeah.
on the previous slide still? So if you do take the known compound, or the compounds for which either omega or lambda is known, and you map it onto these, do they fall on, or they're under the histogram?
Well, if the material is really a true electron-phonon coupling superconductor, the results are usually not so bad. Now, I can tell you, because we did a lot of compounds and we looked at a lot of experimental data, that there is we have to make a lot of effort to understand even simple compounds. I give you an example. Probably 20 to 30% of the compounds that have an experimental TC give imaginary phonon frequencies to start with. Now, I'm sure Ion will be able to solve most of those problems with enharmonic effects, but we don't have them, right? Then I can also tell you that many of the compounds that are in the experimental database have antisites, disorder, vacancies of stoichiometries, and the TC that you have experimentally, I mean, the material science is complicated, right? And sometimes you have to take into account all those things to get the proper TC. So it is hard. Eventually, someone should go through that. Yeah, but it's again humanly. I mean, you will easily spend months per compound sometimes to. Yeah. But anyway, distribution of TC. This is omega log. This is lambda. This is the color is just Macmillan's formula for you to have an idea of how TC changes. And this graph is amazing, right? Look, 50 Kelvin. Here, yeah? So many things. Yeah, even 100 Kelvin. That's wonderful. There's no problem in finding conventional superconductors with TC at 100 Kelvin, even more. Yeah? You see it here. There is no problem. So what is the problem? Who can tell me what the problem is? You cannot make them. That's easy. In the computer, they exist. No, because they're thermodynamically unstable. We'll come afterwards.
That's really a distinction.
Because they're fantasies.
Okay, good. No, that's important.
But I will come at that in 1 minute. In 1 minute. They are not fantasies in the computer. So they are dynamically stable. They are mechanically stable. They have beautiful phonons. They have beautiful Fermi surfaces, everything that you want. And they give high TCs, right? I have a couple of examples here just for you to see. They are two hydrides, but there are other ways of getting high TC. There are essentially 3 different paths that you can go to high TC. We only found 3. Hydrides, boron carbides, and magnesium diboride, and friends. These are the only 3. Immediately after, nitrides. Then come intermetallics. Yeah? So this is the biggest families that you can have. Hydrides are the ones with the highest TC for reasons we all know. This is one of the ones that we have that have the highest TC. Perfectly, well, the phonons are a bit imaginary here, but Ion fixed it by using enharmonic effects. So if you put an harmonicity, these small imaginary things that you see here, they get immediately cured. It's not a problem. We have an omega log that is not terribly high, and a lambda of 4. So it's amazing that something with a lambda of 4 doesn't have imaginary frequencies. Well, it does, but they are cured by enharmonicity, so it's fine. The coupling comes mostly from here. So this flat phonon bands here that have a huge coupling, and plus a little bit here. Another example, so this is not a perovskite. The octahedra are isolated. They are not, they don't share vertices. So it's not technically a perovskite. Well, whatever I don't know what is a perovskite. Ambient pressure. I don't have anything about pressure here in this talk. We can discuss it afterwards if you want. Just to show you another example, this has pyramids. So no octahedra. We have, at the moment, 650 hydrides with the predicted TCs above 20 Kelvin. And you can be sure that the variety is gigantic. There's not a single solution to high TC superconductivity. You can have whatever, literally. It's a lot of variety. So let's go to the problem. Yeah? So we have here distance to the hole, so if you want thermodynamic stability. The scale is 250 millieV, which is huge. Yeah? Here comes TC. This is the Pareto curve, the Pareto front, I'm sorry. So MGB2 is not here. Well, it is, but it's not really here because these are isotropic calculations. So MGB2 is somewhere here. In isotropic, it's, I think, 16 or 17 Kelvin that it comes out with. And what do we see? So up to here, things are thermodynamically stable. Then it starts going bad. So this was our biggest finding, if you want, was lithium molybdenum nitride. This compound does exist. TC has been measured. It's 0. Eliashberg theory says 40 Kelvin. Experimentally, it was already discussed. So this compound was synthesized twice in the 90s. The 90s, I think. Well, some time ago. It was already discussed that there were a lot of antisites. The measured density of states at the Fermi level was 20% lower than the calculated one. It's not clear if it's antisites, if it's lithium that goes into the interstitials. It's not clear. Or it could be something exotic. I don't know. So one thing I can tell you is that Eliashberg theory gives 40 Kelvin, around 40 Kelvin. And this is certainly, the calculations are correct. They were done more than once by more than one person. This is correct. And it's in complete contradiction with the experiment. So I don't know. Everything else that comes here, there are a few more nitrides. I'm sorry, these things are on top of each other. And then these things here are hydrides. You have here a few examples. And then you see the price you have to pay to get a hydride. You have to pay between 50, well, it's between 50 and 200 millieV per atom. That's the price you pay to make a metallic hydride. The lowest hydride, the hydride we have closer to the convex hull, is a palladium hydride. That actually exists, right? I don't remember what is here. I'm sorry. I didn't look. It's I think it's something with thorium, but it's not a problem. So even if from the superconductivity point of view, you can have TCs that go well above 100 in the conventional mechanism, the materials that support it are not thermodynamically stable at ambient conditions. Now, can you make them under pressure and quench them? I don't know. That's what is missing. So maybe I should spend just 1 minute saying what we don't have, because we have a lot. Yeah.
That would seem to be incorporatable into this, or maybe you have disagreements with Lilia. I don't know, but I know that
Lilia, well, we talked a lot. I think Lilia agrees with us that this is very unlikely that you can quench these materials.
no, but it can be calculated. I'm saying so. This is you left it as an open question. It can be calculated. So actually, these have been calculated, or you agree they're unlikely to be quenched.
So there are several parts. First of all, the materials have to be stabilized by pressure enough, and at low pressures, and that's what you would like, because I don't believe you can quench a hydride from 100 GPa to 0. Hydrogens are too mobile. They will leave. Yeah. So it would have to be relatively low pressure. Let's say 10, 20 gigapascal. Most of the hydrides that are stable still in these conditions are insulating, which is also what we would expect. Ion found one, so this rubidium phosphorus hydride, that seems to be stabilized, and it needs an harmonicity to be stabilized. Yeah? Maybe there are more. I don't know. These ones, the ones we tried, were not stabilized enough by pressure. So, yeah. Emilia, I think, raised the arm first.
So the fact that they're insulators may not necessarily be a problem, right? If we can take the next step and calculate how to dope them, if they can be stabilized after the pressure is removed, then there's the next level of computing whether doping would make them metallic, if not superconductor.
So that's actually what I wanted to say when I said I will take a minute to say what we don't have. We don't have doped systems. I mean, we do have some systems that look doped, right? But we do not explicitly change the charge of the systems, right? By explicit doping or just by playing with the Fermi level. We don't have that. We don't have disordered systems. And disorder will probably be important. We don't have an harmonicity. That is certainly very important. Yeah? So there are still a lot of things we don't have. So take this with a grain of salt. Maybe there is a compound that can be doped with 20% of electrons or holes and be stabilized and superconducting. So what I can tell you from all this is that if you want a high TC hydride, the best strategy is to hole dope. I don't think it's surprising for many people. It's a hole dope, although electron doping sometimes works. And you usually need at least one electron in the in the valence to see something. So this is what I can tell you. Oops, I'm sorry. Yeah? Ask, I'm just unlocking this.
So you commented on dynamical stability, and experimentally for the hydrides, the highest TC is found where DFT and quasi-harmonic lattice dynamics show it's dynamically unstable. So I'm worried that you're throwing away information. You have some reason to, like you gave the example of when there is some weak, instability, you can correct for that. But do you have a screening process for knowing what to look for so you don't throw away some of the really interesting phases that may be dynamically unstable to have very high TCs?
So we sent already to Ion all our hydrides that were dynamically unstable. Of course, I don't think it's very hard to go through 70,000 dynamically unstable compounds and magically discover the ones that are stabilized by an harmonicity. Right. But we try, of course. Yeah. So when we have small instabilities, that's easy. But when the whole, for example, the whole branch is in the imaginary sector.
But even some of those are
I know.
Stabilized by Shaw.
Sure, I know, yeah. But I don't know what to do. Well, at the moment, maybe in the future. Let me just finish. Conclusions, finally. So machine learning has accelerated significantly our workflow, sometimes by factors of 100,000, believe it or not. Now, this is maybe a bit controversial, but most relevant inorganic stoichiometric compounds are already in the databases, most. Don't expect magic discoveries of compounds, especially made with first-row atoms. Don't expect that. This will not happen at all. If you want to find something new, ternaries, in and there, it's already hard. Yeah. Then we have gone through large parts of material space to search for conventional superconductivity. So I told you we searched 160 million compounds, which is not infinite, but it's 160 million. We have many high TC compounds, but the high TC compounds are thermodynamically unstable at ambient conditions. And this is from the Kagomez. Flat bands, we didn't find any compound that had flat bands and that really showed extraordinary superconductivity. In those Kagomez, usually it's the wrong atoms that contribute to the electron-phonon coupling, is not the Kagome. And that's unfortunately not the ideal for superconductivity. Now, we have a lot of things to do still. So first, we have to explore the entire chemical space. We will never be exhaustive, but we will, we can easily have 1 billion compounds in the database. That will happen in the next year or so. So that's the objective. And we have to move beyond conventional superconductivity, because even if whatever you do, it will be very hard to get very high TC with conventional mechanism, right? Of course, I don't know how to do this. At least not in the same way as they did conventional, of course. But I've heard a lot of ideas also here, but you have to be careful that these ideas, to be useful in this context, they have to be quantified with the mathematical formula and strict thresholds. They cannot be qualitative assessments, because computers don't know qualitative. They need hard numbers. Yeah, and that's what's really hard sometimes for. And of course, I have to acknowledge everybody. So the three foundations, including the Simons Foundation, that actually pay for most of my work, and the supercomputers and the people. So Tiago in Coimbra, Jonathan in Zurich, Aldo in Virginia, the group of Ralph that does machine learning interatomic potentials, and Silvana in Bochum, and my guys there. Theo is here. He has a poster on the Cagomes if you want to go and see, and thank you for your attention.
Thank you, Miguel. Okay, there are more questions over there.
If you go back to the slide with the Pareto front.
With the Pareto front, yes.
Yeah.
Oh, the other way around. No, not this one.
So do I interpret that right to mean then that really this suggests that it's going to be hard, right? Even if this falls even for high temperature superconductors or other beyond electron phonon or whatever, this is going to be hard because you only have, out of all these data points, you have like 4 or 5 on the line. Is that right?
Yeah.
Good.
So we did a lot of analysis. We spent a lot of time, actually, it's a rabbit hole, trying to find the highest possible TC. And we are absolutely convinced that from the data, not from the mathematics, because the mathematics, if you go through them, probably the limit for TC is 1,200 Kelvin, electron phonon coupling. This is, I think, the mathematically correct number. But from the data, from the alpha square F of omega that we have, the absolute limit for TC cannot be much beyond 100 Kelvin at ambient conditions. Yeah, they're hydrides, and the hydrides, you have to pay a price to make them metallic. They don't want to be metallic. So.
Okay, there is a question from Andy.
Paul, were you following up on that?
No, I wasn't following up different, so go ahead.
All right. So I had a completely different question. I'm not as but I've been hearing complaints from people connected with the protein structure. They started a couple of years after AlphaFold became very successful. Can you use the mic? Can't hear you.
We can't hear you.
We can't hear you, Andy. It says it's on. All right. But the people who are thank you. People who are connected with the protein folding business tell me that within a couple of years after AlphaFold became clearly successful, the rate of submission of new experimentally verified structures to the protein data bank fell essentially to 0. So that, as you mentioned, everything relies on quality of database, and that beyond this point, the things which were submitted were basically things generated by AlphaFold itself. So the whole structure is getting more self-referential.
Yeah.
Do you see any sign of that in the areas that you're concerned with, where you're adding things to databases and?
Here there is not a very big problem because it's DFT data. So the database is relatively clean in that sense. Now, there is a bias that comes because the compounds that are chosen to go into the database, they are generated by machines again. And that's not quantifiable. It's very hard to know. So what we do is that we periodically retrain the machine, starting from random weights, hoping that the systematic errors are different. Now, we are also not isolated. There is experiment, right? And there are people finding materials all the time. And we are just trying to get as much data as possible. So I don't think it's as bad as for proteins, especially because there are no experiments involved, right? This is much cheaper. It's just EFT, but I cannot quantify it.
Well, as you said, some of it is machine learning.
Sure. Yeah, there will be bias that are reinforced, certainly, but we don't know which.
Yeah, and I guess the question is, how does one find it?
Yeah.
Okay, 2 more questions and quick answers. So, Paul?
So, one of the problems I've had is not about TC, just predictive structures. We discover a new ternary, new crystal structure. Okay? We've inverted the process. Rather than asking computational people to predict and guide us, we say, we discovered a new compound. Can you tell us what it is? And the groups I've worked with will do the usual. We tried a million different, we down selected, blah, blah. Here are 20 compositions that are at or below the convex hull. None of them are right. We tell them the stoichiometry, they do it again. None of them are right. We tell them the lattice parameters and then the basis. This is problematic. So there seems to be a problem, at least with the people I'm working with, and I think they are respected in the field, of actually finding a material we know makes. So we've removed the whole question of is it makeable? We've inverted it, and I think this is a very useful benchmarking test. Do you think your program, your algorithm would do well on a test like that?
I think it will depend a lot on the exact compound that you are talking about and the chemical system and a lot of materials details that
Fully stoichiometric, no disorder,
we try
ternary,
it. Give
lanthanum,
it
cobalt, lead. Or I could.
cobalt.
Oh, yes, it's a transition metal. Oh,
Yeah,
my
yeah.
God.
Yeah.
Is,
Let me guess, it's antiferromagnetic.
well, first you would have to guess it's moment bearing or not.
Yeah.
With that little bit of cobalt, often it isn't. But, and again, tragically, we published this structure 2 years ago or a year ago. So would you be able to blind your system back 2 years and then see if you can find it? Because if the answer's already there,
You have to tell me what is the compound, and I will have to go and see if we have it, and
Yeah.
if we do, what is the where it came from.
exactly.
So that's.
But if you need one we haven't published, we have other ones that we haven't published. But I consider this a vital benchmarking exercise for this because it removes the question of can it be made. We made it. It likes to make. It's a new crystal structure. Can you predict it? And if we get enough benchmarks like that, then you get a warm, fuzzy feeling.
Can I say something?
Please.
There is one issue, is that the error in all our approaches is statistical. So you cannot give me one material and tell me you found this one and not that one. You have to give me at least 50, and then we will see what is the probability that we are right or we are wrong.
50 is a lifetime of new discoveries for me.
That's the problem.
But there's many
No,
growers.
no. But to a certain extent, that was a it may have been accurate, but it was a useless statement because that's not something that's doable. But I think it's worthwhile to start trying to collect benchmarks, and we can get various synthetic physicists, chemists, whenever a new crystal structure, not the terbium member where gadolinium and erbium are known, that's boring. But if these algorithms can start getting those, it's good. And if they fail, postmortems would be very useful on a case-by-case basis.
I do agree with you. And I can tell you what our experience. We had successes and we had failures.
And did you do postmortems?
Well, yes, to some extent, yes.
Okay.
But I have to tell you, the successes were rather surprising for me, because the first one was nitride perovskites that didn't exist. We predicted them in 2015, and 5 years ago, the 3 that we predicted were made, and I was not confident at all, because nitride perovskites, and it worked. There are others, intermetallics with Emilia, that didn't work at all. We have other intermetallics that worked, but we don't have statistics even to know why one worked and the other one don't. Because this is DFT. We don't understand where the error comes from.
There's just an advantage to starting with the material makes, because it gets rid of the whole discussion of, maybe you didn't try to make it the right way.
You're absolutely right. You're absolutely right.
Okay, thank you. I promised, I'm really sorry. I will stop here, and very quick question and very quick answer, please. We are already long in the coffee break, and the coffee breaks are very short.
It's not my fault.
Just a comment. I think what Paul proposed exists is called the synthesis bounty board, and you can get 20K or something for your personal money if you.
Oh, I didn't.
There's a bunch of growers that are bringing new materials and a bunch of AI people. It's called the synthesis bounty.
The synthesis bounty.
You can get some personal cash for it if you.
Okay, thank you for everybody, and let's be back at 4 o'clock.